Good morning, everyone. My name is Francesco Ambrogi, and I'm a PhD candidate at Queen's University under the supervision of Professor Ugo Piamelli. Today, I will be talking about my research topic, which is frequency dependence of unsteady separation in a turbulent boundary layer. The motivation behind my research is quite clear from this slide. Unsteady separation is very common in many different systems, ranging from engineering to the human body to the natural sciences. It is very crucial that we understand the physics of unsteady flow separation. In our recent publication, Characterization of Unsteady Separation in a Turbulent Boundary Layer, Mean and Phase Average Flow, we performed numerical simulation of a specially developing turbulent boundary layer in which the inflow condition is taken from an auxiliary parallel simulation at the desired Reynolds number, and the top boundary condition prescribes the vertical velocity profile to generate separation on the bottom, same approach as 9-Moy 1998. The difference in our case is that the V infinity is actually both space and time dependent, composed of a steady component chosen to match the 9-Moy calculation and a dynamic oscillation component in which the most important parameter is the reduced frequency, defined as the ratio of the convective timescale of the flow over the imposed unsteady timescale. LPG here is the length over which the pressure gradient varies. So if we look at U infinity and V infinity in the domain, where V infinity is our boundary condition, you'll notice that at phase 0, beginning of the cycle, the boundary layer feels a zero pressure gradient, and then it goes into a region in which a favorable pressure gradient is followed by an adverse one, and then back to a zero pressure gradient again at phase 180, and then into a region in which an APG is now followed by an FPG. We performed a wall-resolved LES in which the subfilter scale stress tensor has been modeled using the Vreeman eddy viscosity model. We performed simulations for a wide range of reduced frequency, and the oscillation period has been divided in 20 equally spaced phases in order for us to carry out phase averaging for every quantity. So if we look at the behavior of the phase average streamwise velocity contours for the three frequencies, you will see that the oscillation frequency greatly affects the transient separation cycle, which is present in every case. The very slow frequency, K0.2 case, shows a trend toward a quasi-steady state in which now the dimensions of the separation bubble, both height and length, match really well the steady calculation. But the most interesting case is the K1, because we found a frequency at which the separation region is actually unstable and gets washed out of the domain periodically. Now, what we have done so far was characterizing the unsteady flow separation using the mean and phase average flow, and we also described dynamic hysteresis effects in the domain. However, many questions still remain unanswered. How is the reduced frequency affecting turbulent kinetic energy and higher order statistics? And what is the effect of this periodic washing out behavior on the flow physics? And finally, what are the causes behind this washing out behavior in the first place? And this is exactly where I would like to shed some light in today's presentation. So the first result that I would like to show you is that phase average turbulent kinetic energy in the domain. And as the animation plays, you'll notice that for the very high frequency, K10, nothing is really happening in terms of TKE, and it just behaves like a turbulent boundary layer. But for the K1 and K0.2 case, I would like to focus your attention in this region in the domain, because now, even for the K0.2 case, an advection-like phenomenon is present for the TKE. However, it's dynamic, it's completely different compared to the K1 case, in which this high TKE region is actually washed out of the domain while it's keeping its shape. So if we remember that we divided the cycle in 20 equally spaced phases, this means that we have the two zero pressure gradient phases sitting at the opposite side of the cycle. And then we have the red region of the cycle, or the acceleration side, containing all the phases in which U infinity is greater than 1. And then we have the separation side of the cycle, or the blue region, in which all the phases have U infinity less than 1, and the flow separates around phi 270. Now, with this knowledge in mind, we can actually evaluate turbulent kinetic energy in the washout region only. And you'll notice, if we do this analysis for the K0.2 case, that this high TK region in the front of the bubble is generated due to the separated shear layer, and it grows and shrinks in the wall normal direction, but doesn't move in space. There is this high TK region in the back of the bubble generated due to the flow impingement on the wall, and there is a clear transfer of TKE from the front to the back of the bubble and out of the domain. And all of this happens in the separation side, the blue region of the cycle. Now, if we do the same analysis for the K1 case on the other end, you'll notice that this high TK region actually grows in the wall normal direction in the separation side of the cycle. And it doesn't start moving until the free stream condition changes around phi 0. At that point, this high TK region actually starts moving, and the most interesting fact is that it's keeping its shape. It's not deforming. So the three questions that rise now are, is it moving at a constant speed? Is it a rotational structure? And why does it keep its shape while it's moving downstream? So to answer the first question, what we did was analyzing turbulent kinetic energy contours for the K1 case as a function of the streamwise direction and phase. And you'll notice that for three different wall normal position, very close to the wall, in the middle of the separation bubble, and further away. And you'll notice that the slope of these contours, which is a footprint of the advection velocity, are parallel to each other no matter where you are in the y direction, meaning that this advection velocity is actually constant, and we evaluated it to be 0.6 the free stream velocity. With this knowledge in mind, we can answer the second question and visualize the relative velocity field to answer, is it a rotational structure? And if we do this for the K1 case, for 4 consecutive phases after the structure starts moving, you'll notice, and here the black shadow underneath is turbulent kinetic energy, you will see that this is indeed a rotational structure. Not only that, but the high TK region corresponds to the region of the flow in which this velocity vector go up and around the bubble, the structure. And this red dot corresponding to the center of the separation of the structure actually is always a little bit upstream of the high TK region, but its distance with respect to the wall doesn't really change much, and it's sitting on a straight line for 4 consecutive phases. So now finally, why does it keep its shape while it's moving downstream? So to answer this question, what we did was analyzing average particle path lines. So in a statistical sense, this is the average position of a particle as it moves downstream. Now, here is important because with the knowledge that for an unsteady calculation, for an unsteady flow, streamlines and path lines are not equivalent, we can actually choose a particle, some particle positions and seed them inside the separation region and observe as they move downstream. If we do this analysis for the K0.2 case, where again the black shadow is the turbulent kinetic energy, you'll notice that particle path lines just behave like streamlines. They do whatever the free stream is doing. So here, for example, there is suction, they go up, there is blowing, they go down, and they are all out of the domain pretty soon in the separation side of the cycle. But if we do the same for the K1 case on the other end, particle path lines do cross each other, and they do so in the acceleration side of the cycle. Not only that, but if you pick 2 specific particles, you'll notice that these 2 particles are starting doing whatever the free streaming is doing, so they go up and down. But then once the free stream condition changes, actually they are stopped towards their path towards the wall, and they start moving upwards, corresponding exactly at the center of this high TK region. Now, to visualize this a little better, we can actually overlap path lines to the vertical velocity profile and turbulent kinetic energy. And you'll notice as the animation plays that there is a pocket of particles that no matter what the free stream is doing, they always feel suction. So they keep moving upwards. And this is because they are slow enough, they're fast enough to escape the wall effect, but slow enough that they can feel what happens at the free stream. So in conclusion, we performed simulations for a wide range of reduced frequency, and advection-like phenomenon was observed for the K0.2 case, but its dynamic is completely different compared to the K1 case. And for the K1 case, this structure is advected at a constant speed and is rotational. Particle path lines shows a trend towards a quasi-steady state for the K0.2 case, but for the K1 case, they do cross each other, and we have shown that a pocket of particles is picked up and start moving downstream with the structure. So in future, we are trying to calculate forces involved with this advection process, and we would like to study them, the frequency dependence of this phenomenon. We would like to explain the different dynamic behaviors observed for the K1 and K0.2 case in terms of this advection process, and also would like to look at structures, turbulent structures, as a function of the reduced frequency. This is all for me. I thank you very much for your attention, and I'm ready to take any questions.